This is video homework number 4, problem number 4 for Tim Barron, Physics 350. We've got a metal sphere with radius large r carrying charge q, and it's surrounded by a thick metal shell. And what they want us to do is find the surface charge density at different radiuses, find the potential at the center using infinity as a reference point, and then pretend that the outer surface is touched by a grounding wire and see how the answers change to parts A and part B. For the solution, I'm going to start by creating a clear diagram showing all the radii and charges, and then I'm going to use the formula listed. So what we can see here on the diagram are the 3 different radii. We can see big R, A, and B. And then in the center we have the sphere with charge Q, and we can see that in the shell the charges have split to where Q minus is on the inside surface and Q plus is on the outside surface. Then using the formula for surface charge density, which is Q over 4 pi times radius squared, we can see for each of these what that would be. So for part B, they want us to find the potential at the center using infinity as a reference point. And you can see the formulas that we're going to use to do this, and we need to figure out what the electric field is to be able to plug it into the potential formula. So we're going to go ahead and look at the electric field at the different radii, and what we can see is it's going to be 0 when R is less than big R, and when R is greater than A but less than B. And then when R is greater than big R but less than A, it's going to be Q over 4 pi E naught R squared, and the same thing when R is greater than B. Then when we go to find the potential, we're just going to need to use the limits from infinity to B and the limit from A to big R to find out what the potential is. Now for part C, they want us to pretend that the outer surface is touched by a grounding wire, which drains charge off and lowers its potential to 0. They want to know how the answers to A and B change. So the answer to A is the same for at big R and A, but at B it now becomes 0. And the answer to part B changes in that now the only one that has an electric field is when R is between big R and A, but not equal to either. So we'll see there when we do the potential equation, we only need to integrate from A to big R. So to solve for this problem, I created a diagram and I used the 3 formulas shown here. But overall what I learned was that by thinking about Gauss' law and the enclosed charges, I can eliminate parts of the integral, which made this easier to solve by just looking at what was going on here.